ACE 111 Lecture 4 and 5 Set 4, System Verilog Data Types. In terms of the RTL modeling, we could have a 4-value set to represent the actual value. And we've seen this before in earlier lectures. And we just don't have the 0 we just don't have the 0 and 1 like we have in the regular logic. We also have the high impedance and don't care, which is basically an uninitialized value. What happens is that this would translate later using the software into a 0 or 1. This is not going to be kept dangling. The system Verilog data types can be specified by the design intent. Typically, one thing we have is the data kind or type, and the other one is the data type, and this can be distinguished. And what I mean by that is, if you're talking about just the kind could be, we just either have a wire in the design or we have registers in the design, and this is just a simple distinction. But wires by themselves could have different instantiation, or nets, they have wires, but there are other constructs that are kind of more specific. We could have tri-state and so on, that we could define nets. And variables are typically just defining for us register. Now, after we have this kind, what we are going to store in this kind is a data type. And the data type, it can be two-state, like a two-state logic, like bit, byte, or integer or long integer, or it could be a 4-state, like if you define register, you could assign any of the 4 states we've seen earlier, like 0, 1, X, or Z, to that register. And the time is also a 4-state value. Logic is also a 4-state value. For the data type, because System Verilog helps us to have higher level of abstraction, the other thing we could even define real number, and the real numbers is another data type that we could be using in the System Verilog. In short, any data can be declared using the syntax, the kind, like a variable or a wire or a net, and the data type, which we've seen here, like, is it logic, is it a register, is it integer, and the literal name. In this case, we are talking about this as an address. All possibilities for the System Verilog are listed in the figure here, and as you see here, these are actually synthesizable, meaning that this is going to be synthesized, and all these 3 are synthesizable, but whereas a real one is not necessarily readily synthesizable to hardware. So in summary, we have nets and variables, which we are showing here, and they could have both a type and a data type, and the data type could be a 2-state or a 4-state, and typically the 2-state data types have better simulation performance over a 4-state, but they may lead to bugs, as you will see later. And the data types are used for both simulation and synthesis, how to determine how to store and process the data, and they just also indicate desired silicon behavior. For example, if we have an ALU with floating point, it makes a difference how it's going to be translated into an RTL model than an integer type. Let's just see more details about the net data type. It's basically a net as you would describe it. It's kind of a wire connection, and that's why it doesn't store any value. It is continuously driven. The wire construct is the most common type of a net, but there are other types of nets that are possible that we could define in System Verilog. You're welcome to look at the descriptions if you're interested to use them, but you could also define the strength of these these nets, if they're high impedance, low impedance, if they're kind of larger nets or smaller nets. And they can also sometimes take modifiers. For example, we can talk about vectoring them, signing them, and so on and so forth. The wires which are the most representative of the net family are basically, again, using for connections. They cannot store values. They cannot be used on a left-hand side of an equality or any assignment in an always at block. So they're they're stateless, and they can only be used for modeling the combinational logic. They cannot really store values, and that is clear why it cannot be used for this. If you look at the example here, the left-hand side for inside this always block has to be either register or logic. It cannot be wire. And but assign, which is a combinational, the left-hand side should be a wire, which is here. The wire is a result. A variable is showing a storage element in the circuit. And when we define variable in a higher level abstraction, it does not necessarily mean that we're going to translate it into a register. But register, when we use it in a higher level construct, that means it's going to model the hardware register. But it could also define logic, because inside the always at star block, as you've seen before, we could define a combinational logic. The default value for a register is a don't care, but it must be used when modeling sequential elements. So this is the typical way how we use this. Now the register could have different values, and some of these are synthesizable, some of them are not. If you're storing a variable that is that you want to synthesize, it should take the format of a synthesizable variable, such as a logic or integer or byte or bit. And the reason here is that these are directly translatable to zeros and ones in terms of the logic. If to ease the programming, there are non-synthesis variables. For example, if you're defining a floating point ALU, you could define it with variables and assign real numbers to them, but they are not necessarily synthesizable because it's not an exact interpretation to zeros and ones. So these are the non-synthesizable variables that we see on this slide. More on registers. Registers can be connected to the input port of a module, but they cannot be connected to the output port of a module. Now they could be used, when you're actually making a module declaration, they could be using them as output, but they cannot be used as input when you're declaring an actual module. This is the only legal type on the left-hand side of an initial and always block. And if you remember from what we described earlier, initial and always, they typically define sequential logic. They could also mean, if you have always at and the sensitivity list for any of the signals, you could use it to define combinational. So registers can be used for creating combinational and sequential logic, but if you're talking about the initial block, the registers are the only legal type on the left-hand side. Even for the always at, this is the only legal type on the left-hand side. Then, if you have the always at positive h, then we're talking about the real registers. But if you're talking about always at, for example, star, then we are talking about registers as a combinational element. Here we see an example of a register module that we are using here in the in the left-hand side, which has to be either a register or logic if you're talking about a positive edge or a sequential logic. This slide is showing the difference between Verilog and System Verilog in terms of the wire and register usage. Verilog used to be very restrictive about where this wire and register data types has to be used. In particular, we could only using it on the left-hand side of the continuous assignment statement, and registers could not be used for input and output in-out port declaration. In System Verilog, they kind of relaxed that requirement. You could use it for port and signal declaration, but in Verilog, the support for the variable that could be synthesized was only for 4 state variables like that are using all these particular types. In System Verilog, they kind of relaxed that. You could also use 2 state variable which has 0, 1 type. And the reason for this is that if you define 4 state, you're going to use in the simulation a lot more space because there is more possibilities. Whereas, for example, in testing, sometimes we only care about zeros and ones, so it makes the simulation much faster. You don't really need the X and Z's, and this improves the simulation performance. Here's more syntax for System Verilog versus Verilog data types. I'm not going to go through the details of each and everything on this table, but if you ever need to reference to something, you're welcome to look at this slide. The inference for this has some general rules. Again, the rules can be just kind of boring if I just go ahead and read about from the slides. But take a look if you want to use this in 2-state or 4-state variable in your program. Kind of you could refer to this, and some of them are common sense. For example, the bit is a 2-state variable, as you would expect. Wire is a 4-state variable. The register is a 4-state variable. Logic is a 4-state variable. And you had that information on some of the previous slides as well. Here is just a summary for you if you want to take a look at this and figure it out. More kind of detailed explanation and examples here. Again, if you're writing a program, it's useful to come to these and look at the number of states and how each of them are declaring the combinational or sequential variables in our design. Let's go through some recommendation on data type usage because I think that's the most useful we will have from this course. Here is a summary of the recommendation. The typical recommendation is to use the logic data type for all declaration, including for ports and internal signal, and then you kind of let the language decide if it's going to be a net type or a variable type based on the context. And this way we kind of avoid a lot of problems. If you kind of need to do point-to-point nets, variables, input ports, and output ports, this is what is recommended nowadays. If you're writing an RTL model, avoid the 2-state data type, and this is because if you define the 2-state data type, there is a difference how simulation and synthesis are going to interpret that, and that could lead to design bugs because we typically do both simulation and synthesis when we do real design. Here, for example, if you talk about the bit, byte, and all that, it's a 2-state data variable, and then 4-state, this can be interpreted in synthesis as a 4-state register variable, but in simulation, this is all treated as a 2-state variable. So what happens is that you will see discrepancy between the two, and then this could get to difficult state. The only exception is when we are using a loop. So in loop variable, the iterator variable in the 4 loops can be a 2-state variable in the RTL model. This slide shows a summary for the differences between wire, register, and logic, what we've described earlier. If you want to just have a side-by-side comparison, please go through this. Integers are typically a four-state variable, and for synthesis, it's usually used for parameters that take integer values like constant and so on. They are implicitly of the type registers, and we have the keyword integer, but they could be used for sign numbers, and the sign is typically defined using a 2's complement, and you could have at least the 32 bits if the size of the integer, but you could, if they hold constant, you could change the size, so kind of have that in your implementation, taking less space. Let's take a look at an example here. If you say just integer data, it's going to declare it as a 32-bit integer, but if you just say assign b is equal 31, because this is a constant value, it's going to be treating b as a 5-bit integer, not a full 32-bit integer as we would have for a generic integer type. We've mentioned time before. Time is really only used in a simulation and not in actual hardware. You could define a 64-bit data type, which we use in conjunction with $time to talk about the simulation time. And this is the syntax is very simple. You just have time and the variable name. Here is an example. So if we have the time start t, what happens is that we are going to start timing, and then this would be declared as a timing in simulation. We could also have the real construct. Since System Verilog is a higher level language, it gives us also the capability of defining real numbers. These real numbers can be declared using the keyword real, as can be seen here. But if you assign this real value to an integer, then it's going to concatenate this real value to the closest integer. And because it's not an integer value, it's not going to be containing don't care or a high impedance value. And this is not a hardware synthesizable construct. It's only for simulation purposes. The real variables could be specified either using decimal or scientific notation. Here is a decimal notation. Here is a scientific notation. And the syntax looks like just real variable name. Using the example, we could just have real height, and you could even assign a real number to the height, which is not easily synthesizable to hardware, but you could use this to declare values to the variables in your program. In the next set, we will be talking about conditional operator and the continuous assignment statement.